Hello, I'm Jover-Alvarez, recent master's graduate from Universitat Politècnica de Catalunya and junior researcher at Barcelona Supercomputing Center. This work is a student project performed during my master's studies in collaboration with the European Space Agency within the GPU for Space ESA project. The project I will present is about the acceleration of space compression algorithms on embedded multicore and GPU platforms. In recent years, we've seen a demand of computing power in onboard computers for satellites, rovers, and spacecrafts. This is due to the fact that the space systems require to perform increasingly complex tasks with larger sensor sizes. While the amount of onboard data is increasing, the communication bandwidth remains limited, therefore compression algorithms need to be used. In addition, current space processors are unable to provide the required performance of all this complex processing. When this happens, they require functionalities implemented on FPGAs. However, hardware design is more complex compared to software development. Therefore, there is an interest in alternative high-performance processing solutions for use in space. Among the potential candidates for future high-performance processing solutions, we can find embedded systems on chip with GPUs. These little but powerful devices have been designed for use in other critical domains, such as the automotive industry, and come with a set of features which are ideal to accelerate almost any problem. They feature multiple CPU cores and embedded GPUs with several shader cores, offering a large amount of parallelism which is easier to explore compared to FPGAs, using programming models such as OpenMP for the CPUs and CUDA and OpenCL for the GPUs. Moreover, their high performance capability comes at low power consumption between 10 and 15 watts, which makes them possible to be used for onboard processing. In the GPU for project funded by ESA, we are exploring that direction. This project is coordinated by the Barcelona Supercomputing Center and it's performed in collaboration with the Airbus Defence and Space Onboard Processing Department in Toulouse. The project aims to study the feasibility of embedded GPUs for future space missions. If you would like to know more about this project and what we have achieved so far, feel free to check the FSW 2022 talk GPUs in Space. Are we there yet? Benchmarking is an important part of the work we did, but we had a problem when we first started the project. There wasn't any representative space benchmark suite for GPUs. For that same reason, we decided to design and develop an open source GPU benchmark suite for space, in which we compiled different building blocks used in several domains based on a space software survey performed with Airbus Defence and Space. With these building blocks, we're able to reach maximum domain coverage with reasonable effort. In this benchmark suite, we find algorithms like matrix multiplication, matrix convolution, fast Fourier transform, finite impulse response filters, and others. In addition, every algorithm is implemented using multiple programming models like OpenMP, CUDA, or OpenCL, and it also includes vendor-optimized libraries like BLAS. We call this benchmark suite the GPU for Bench or OBPMark Kernels, since it evolved to cover any onboard data processing devices, not only GPUs. Next, we developed OBPMark applications, which includes onboard case studies using the building blocks we have developed. Both benchmark suites are open source and co-hosted in the same repository. For more information, feel free to check the OBPMark pre-recorded presentation at Flight Software Workshop this year. In this presentation, we focus on the compression building blocks of the GPU for Bench and the CCSDS compression algorithms that we can find in the OBPMark benchmark suite, among the other complex onboard applications. We have developed several lossless and lossy compression algorithms as described by the Consultative Committee for Space Data Systems specifications, namely the 121 and 122 compression standards, and the 123, which is currently under development, but shares a lot of common parts with 121. When we first started working on the development and evaluation of our benchmarks, we prioritized the algorithms which have favorable characteristics for multicore CPUs and GPU parallelization. In particular, GPUs and homogeneous parallel programming models for CPUs provide high performance under certain circumstances. However, the compression algorithms are challenging when it comes to parallelization, since these problems have a very sequential nature with low regular parallelism, small block sizes, and several dependencies. For this reason, they are a very interesting case study to evaluate the parallel performance of GPUs and multicore CPUs. In our implementation, we decided to implement three CCSDS standards, the CCSDS 121, 122, and 123. Currently, we have implementations of the first two, and the third one is under development, which is a superset of CCSDS 121. The CCSDS 121 provides lossless compression of 1D data. A stream of data is coming in, we encode it in many different ways, and the encoding that results in highest compression is selected as the output. Thus, our compressed data will be composed by streams of data accompanied by their encoding ID, so the process is reversible. The CCSDS 122 provides lossless and lossy compression of 2D data, and it employs the 2D discrete wallet transform and a Bit-planar encoder to reduce the size of the input data. The lossy compression can be performed by employing integer arithmetic over the input data instead of floating point that is used for lossless compression. Like the rest of the algorithms in our benchmarks, we provide an implementation in sequential CPU, CUDA, OpenCL, and then a multicore one in OpenMP. Also, it is relevant to note that we implement only the encoding part of the compression, as we consider it the most representative part of the payload processing. Now, let's see an overview of the CCSDS 121. This algorithm consists of two main blocks, the preprocessor and the encoder. The preprocessor is in charge of simplifying the input values so that they are closer to zero using a series of reversible heuristics. This happens mainly because values closer to zero often compress better. The other block that composes the CCSDS 121 is the encoder, which, as we said previously, implements a series of encoding algorithms, and the one that compresses the most will be selected for that block of data. In this slide, you can see the algorithms we have implemented, which are specified in the 121 lossless data compression bluebook provided by the CCSDS. The parallelization approach we followed is the following. Since the maximum block size which is specified by standard is too small in order to exploit intra-block fine-grained parallelism, we have followed a coarse-grained parallelization approach. For this reason, we added something that we call step, each of which is composed by a series of locks. We did this because any transmission can be split in blocks of independent data. Since blocks by definition are dependent between each other, we wanted to add an extra layer of independency. So intuitively, we can parallelize at the step level, and doing a bit of trickery, even at a block level. But due to the sequential nature of the algorithm, we found that it is more beneficial to perform coarse-grained parallelization at a step level. This is the general scheme of the CCSDS 121 compression. As we commented before, a stream of data comes in, the preprocessor normalizes it, and then this normalized output enters the adaptive entropy encoder. Then, the adaptive entropy encoder runs all the encoding algorithm and selects the one that compresses the most for the input data stream. Finally, the compressed data plus the ID identifying the selected encoding algorithm is returned. Starting with the CPU multicore parallelization, we followed a coarse-grained approach in which every core executes the full CCSDS flow of independent batches of data which we call steps, which are then joined as a stream of compressed steps. We also experimented a fine-grained parallelization scheme at a block level, but the coding algorithms were so simple that the fork join overhead was making the execution time worse than a sequential implementation. Thus, we opted finally for the coarse-grained approach. In the case of the GPU parallelization, it's a little bit different. In this case, we can have two levels of parallelism, the stream level and the thread level. In the NVIDIA GPU terminology, a stream is a FIFO structure in which GPU operations are submitted, and they are guaranteed to be completed in order. However, GPU operations from different streams can be executed in parallel if there are enough available GPU resources for the execution. First, we run the preprocessor in parallel for each step. Each GPU thread is processing a single block. Once we have all the results ready, we launch as many streams as the encoding algorithms we have. Each encoding algorithm is encapsulated in a kernel, which is a GPU computation in GPU terminology. Once all these kernels finish executing, we sync with a barrier, and then the encoding selector decides which was the algorithm that achieved higher compression. Now, let's move on jump into the CCSDS 122. The CCSDS 122 compression is based on the JPEG image compression standard, so it uses a 2D multi-level wavelet transform, which decomposes an image hierarchically in a pyramidal fashion into 4 sub-images. The top left one contains the highest amount of information, which is known as DC components, while the rest, which add only extra information, are known as AC components. The wavelet transform can be implemented in integer or floating point, depending whether lossless or lossy compression is needed. We implemented both. Next, the Bit-planar encoder is used for encoding the DC and optionally the AC components. In our implementation, we only implemented the DC encoding, leaving out the AC one. In our implementation, we first added a random image generator and we programmed and parallelized the following blocks: the 2D wavelet transform, and in the encoding, the DC components and the stream block building. Both of these are essential to further reduce the amount of data to be transmitted. Although coarse-grained parallelization is possible, we opted to go for a fine-grained approach to avoid the memory overhead of large images, since in this case we are targeting 2D images. In CCSDS 122, the data to be compressed is an entire image frame. So what we did is dividing the problem in independent basic building blocks and focus on parallelizing each of them. One of the most challenging parallelizations of this algorithm is the 2D discrete wavelet transform that we parallelized using two 1D wavelet transform, one for columns and another one for rows. When it comes to CPU parallelization, we have nested parallelism. At coarse level, we have run in parallel the computation of each 1D wavelet transform, and at inner level, we have fine-grained parallelism for the computation of each element, so our fork join model, in this case, is hierarchical. Similar to our OpenMP implementation, the GPU follows the same strategy. The main improvement is in the 2D wavelet transform, where we can divide each row to be executed in different streams and each thread to process a different element. In here, we can see the same behavior in detail. The parallelization approach for the other three parts of the algorithm is very similar in GPU and CPU. For the image post-processing and transformation, we need to regroup the data to create the block strings. In this case, it's easy. We work in a value per thread basis. And in the case of the building of the block string, we need to take the regrouped data output from the image post-process and create the different blocks that the Bit-planar encoder will use. Again, this time we only need to split data, which we can do natively with a parallel scatter operation. In terms of the Bit-planar encoder, as we said at the beginning, we only implemented the DC coefficient encoding. Since this process has a very sequential nature, we only compute in parallel per each segment. Thus, we are not really exploiting much parallelism in this part. Now, let's take a look at the experimental setup. We have opted to target two embedded boards which have been selected as the best cost candidates for the GPU for S project. The Jetson Xavier from NVIDIA has ARM-based CPUs. Its CPU, codenamed Kernel, is a custom-designed core from NVIDIA, and it is compatible with the ARM v8.2 specification. The second platform is the embedded Ryzen V1605B from AMD, based on an x86 architecture. Regarding the programming models we have used, in the NVIDIA Xavier we used CUDA for the GPU and OpenMP for the CPU part, while in the AMD Ryzen board we employed OpenCL for the GPU and OpenMP for the CPU too. Next, let's take a look into our target hardware a little bit more in detail. The NVIDIA Xavier comes with 8 kernel cores, based on the ARM 8.2 specification. For the experiments, we used only 4 of those 8 cores, for fair comparison with the AMD platform, which features 4 cores. In terms of the graphics card, the Xavier GPU follows a Volta architecture with 8 SMs, which is the equivalent to the CPU core in the GPU terminology, each of which is massively multi-threaded. In terms of memory, our Xavier has 16 GB of main memory, which is shared between CPU and GPU. For the experiments, we decided to set the Xavier at a low power mode of 15 watts from the different ones it offers. The AMD board comes with 4 x86 core configuration, each of which has 2 threads. Its Vega-based GPU has 8 compute units, which is another terminology for the GPU shader cores for the non-NVIDIA GPUs. Its 16 GB of main memory are shared between CPU and GPU, as in the case of the NVIDIA Xavier. Since this board does not come with a predefined power mode from the manufacturer, as in the case of the NVIDIA Xavier, we have created an equivalent power mode with the 15 watts mode of the Xavier, by setting similar values to the number of cores, CPU, and GPU frequencies in order to have a fair comparison. It is important to note that since OpenCL was not officially supported by AMD on this device, we used a custom driver provided by BraunSpace AB to run our experiments. Now, let's take a look at the results. First, starting on the CCSDS 121. In this case, we executed the experiment with all the J values allowed by the algorithm, which correspond to the block size of the algorithm, which can be 16, 32, or 64 samples. This value represents the number of samples in a block. Our sample size is set to 3 bits, and we used 256 blocks over 16 megabytes of randomly generated data. In total, we have 1024 steps, which is where we'll perform the coarse-grained parallelization we mentioned before. Our results are averaged over 100 executions. In this figure, we present the results in megasamples per second, so higher is better. Looking at the results, we can notice that the multicore OpenMP implementation on the AMD platform overshadows both the sequential and the GPU implementations. That is due to the fact that the CCSDS 121 is a very sequential problem and it is more efficient for processing on latency-based architectures. Therefore, we cannot benefit much from a throughput-based parallelization scheme like the one present in the GPU parallelization approach. OpenMP in this case wins because we introduce the steps factor which exploits in a broad way the algorithm and we are able to execute 4 steps at the same time, as many as the CPU cores. Therefore, the parallelization theoretical speedup without accounting for the 4-gen overhead would be 4x, and as we can see in the case of the Ryzen platform, we are pretty close to that speedup target, which is a great indicator of a good parallelization scheme. Another relevant conclusion is that the x86 architecture of the AMD is more powerful than the ARM architecture of the Xavier, both in single-core and in multi-core performance. As for the GPU, we can see that in the Xavier it ends up slightly faster than the CPU sequential version, but this is not the case on the Ryzen platform. In addition, in all the cases, we see that the maximum performance is obtained with 16 samples per block. For the CCSDS 122 evaluation, we use both real and synthetic images of different sizes. Again, we present the result of 100 executions and we present the results corresponding to the floating point implementation of the discrete wavelet transform, since it didn't have much performance difference with the integer one. Our performance metric is megapixels per second, so again, higher is better. In the case of the CCSDS 122 algorithm, the trend changes as now GPUs seem to be better than multi-core CPUs for this task. That is because the wavelet transform can benefit from a throughput architecture, such as a GPU. As we can see, the NVIDIA Xavier gets very high performance and it scales well with the increase of the image size. In this case, again, the OpenMP execution is running with 4 cores, and we can see a slight performance increase in the multi-core version compared to the single-core one, but not much. Recall that the OpenMP parallelization we opted for is fine-grained, therefore it doesn't give us much speedup. Another interesting point to comment is that the OpenCL implementation overhead at transferring data between the GPU and the AMD CPU is very noticeable, which is why the timings in that platform are very low, even lower than in the sequential version. We expect that this is because of an issue in the unofficial driver we use, so we would like to try it again when official support from AMD will be available for this embedded GPU. In conclusion, embedded platforms with multi-core CPUs and GPUs can accelerate several space algorithms, including challenging ones like CCSDS compression. Then CCSDS 121 is more appropriate for multi-core CPU parallelization, and as we can see, the x86 CPU cores of the AMD platform are way more powerful in both single and multi-core performance compared to the custom R cores from the NVIDIA Xavier. And as for the CCSDS 122, it's more appropriate for GPU parallelization in this case. The NVIDIA GPU provides a very good speed up for the CCSDS 122, and finally we found that OpenCL on the AMD GPU has the worst performance in the CCSDS 122, but we cannot consider this conclusive as we are using a custom version of the driver and not the original one that AMD will provide probably in a near future.